Long before we had telescopes, the ancient Greek philosopher Democritus proposed that the universe was filled with boundless rocky worlds. He imagined places devoid of water, plants, or animals, entirely inhospitable spheres suspended in the void. Humanity finally saw one of these landscapes in 1609. When Galileo pointed his optical telescope at the moon, he didn't find the perfectly smooth, polished orb that early astronomers expected. He found a heavily cratered, jagged topography that looked surprisingly like the face of the Earth itself. But observing through a lens quickly hits a wall. A telescope allows you to map a planet's brightest surface patterns and track its atmospheric weather, but the internal mechanics and physical composition of that world remain entirely hidden. To bypass that limitation, researchers combined astronomy with the earth sciences. They built an entirely new, highly interdisciplinary field known as planetary science, assembling a toolkit designed specifically to map untouchable worlds. If we were going to understand how celestial bodies form and decay, we had to stop treating them as distant points of light and start analyzing them as physical, mappable systems. That analytical process required leaving Earth. By launching robotic space probes, scientists could finally move past telescopes and directly capture high-resolution topography of the worlds next door. This produced the subfield of planetary geomorphology. By reading the sequence of overlapping impact craters, ancient river channels, downward lava flows, researchers reconstruct the planet's physical timeline. During the Apollo program, researchers stitched together overlapping orbital images to create the first stratigraphic maps of the moon, preparing crews for the terrain they were about to encounter. This advanced preparation allowed astronauts to step onto an extraterrestrial surface and immediately execute precise field geology, knowing exactly which rock formations to sample. Through surface mapping, a chaotic alien landscape becomes a highly readable, layer-by-layer timeline of cosmic history. Cameras and surface tools still have a massive blind spot. They can only look at the outermost crust. They cannot penetrate the rock to reveal a planet's core or the tectonic forces turning underneath. To map the interior, planetary geophysicists track the subtle shifts in a spacecraft's acceleration as it orbits. These tiny variations in speed allow them to measure and map a planet's invisible gravitational field. Lunar orbiters recorded specific gravitational dips in the 1970s, revealing dense mass concentrations, mascons, buried beneath impact basins. Applying planetary geodesy, comparing Earth and Mars, shows Mars's extremely weak gravity allows the Olympus Mons volcano to reach 27 kilometers without collapsing. By charting invisible force fields, scientists can deduce the hidden structural limits and tectonic engines of worlds they cannot possibly drill into. The highest resolution planetary map requires holding a physical sample in a terrestrial laboratory. During the Apollo missions, astronauts returned with 384 kilograms of lunar regolith, delivering an exhaustively detailed chemical record of the moon. For bodies we cannot reach with crewed missions, the solar system delivers its own samples. Pristine meteorites gathered from the ice of Antarctica serve as a natural sample return mechanism. In a process called cosmochemistry, researchers isolate unique isotopic signatures inside these meteorites to trace them directly back to their parent bodies. The head meteorites, for example, have been perfectly matched to the asteroid 4 Vesta. Cosmochemistry brings the grand scale of the solar system down to the microscopic level, placing tangible fragments of distant worlds directly onto a laboratory slide. Through geomorphology, geophysics, and cosmochemistry, our own solar system has transitioned from a blank void of unresolved dots into a rigorously cataloged set of evolving geological and atmospheric systems. Researchers are now pushing into exoplanetology. They take this exact analytical logic and apply it to strange, completely unreachable worlds orbiting distant stars. When science fiction author Frank Herbert wrote Dune in 1965, he introduced the concept of an imperial planetologist, a specialized scientist tasked with overseeing the deeply interconnected resources of an entire world. Herbert's fiction closely mirrors the reality of modern planetary scientists. To understand how a whole planet functions, these researchers must synthesize ecology, geology, and meteorology into one coherent picture. We map the infinite variations of dead, frozen, and toxic spheres across the universe for a highly practical reason. Studying how these alien environments form and decay teaches us exactly what it takes to understand, manage, and protect the incredibly fragile living systems of the one planet we call home.